Good morning, everyone. I would like to thank the organizers for the opportunity to speak at this very interdisciplinary and exciting conference so far. So what I'm going to tell you about today is the latest and greatest in what's happening on exoplanet atmospheres. Unfortunately, we are still away from detecting atmospheres of habitable planets. So if that's what you wanted to hear about, we are not going to get there anytime soon. But what I will tell you is a realistic status report of what we can learn about chemical compositions of exoplanets, most of which will be giant planets. We'll start with giant planets, and I'll tell you what's the limit on getting observing atmospheres of super Earths. And then only the first few slides will be a quick review of observations because there is a later talk today by David Ehrenreich who will go into more detail on observations. I will talk about the theory part, the what you can do with those observations, what you can learn about these atmospheres, and a little bit about interiors and formation and things like that. Okay, so let's get started. I always like to start with sort of a going back to the first detections of exoplanets around Sun-like stars. There have been other planets discovered around neutron stars and so forth. But for Sun-like stars, the first planets discovered, as most of you would know, were hot Jupiters. These are giant planets sitting right next to their host stars, about a tenth of the distance Mercury is to the Sun. Okay? So this is very different from our concept of giant planets in the solar system. Okay? And in just about 20 years, we are here today. Today we know of habitable planets around nearly Sun-like stars, in exoplanetary systems. Okay, so this is one very recent example of a nearly Earth-sized planet sitting in the habitable zone of its host star. Okay. So this is sort of the progress we have made on the observation, on the detection front. So we have gone over a wide range of planetary architectures to date. And this is just a summary of the range of radii we have detected so far in the solar system. For the longest time, our concept of planetary sizes was quantized between giant planets, gas giants, ice giants, and Earth. 1 Earth radius, 4 Earth radii, and roughly 10 Earth radii, and we didn't know if planets existed in between those size ranges. Of course, when exoplanets came in, this is just showing the Kepler results. There are other results in the field as well. But you can see that there is really no quantization in radii. All planets come in all sorts of shapes and all sorts of sizes. So this is the summary plot on sort of the diversity of macroscopic physical characteristics of exoplanets. Today we know that exoplanets come in all sorts of sizes, as we saw in the last slide, but also in all kinds of temperatures. So you can see all the solar system planets lie right here below about 300 Kelvin, whereas exoplanets go all the way up to 3000 Kelvin. So that's the upper higher temperatures here are close to the temperatures of low mass stars, basically. Okay, so that's the diversity we are seeing in these planets, and these are sort of some orbital characteristics of planets out there. And I've already talked about how we find hot Jupiters, and there is also a strange class of planets called super Earths that are between the size range of Earth and Neptune in the solar system. So we have no concept of what these planets should look like, what their atmospheres and interior should look like. Okay, so just from planet detections, we know that exoplanets are extremely diverse in their physical characteristics. The question in the field right now, as I would like to think, is what is the chemical diversity of these planets? Okay, we know how they're diverse physically. Now let's look at their chemical compositions and see how diverse they are. So this is where exoplanetary atmospheres come in, because that's our first window to the chemical compositions of these objects. So in the rest of my talk, that is what I'm going to focus on: how we detect the chemical compositions of these atmospheres, and what are we going to learn from them. Okay. I'll have to give you a little tutorial just in case you didn't know already. Most of the atmospheres detected so far have been detected using the transit method. In this case, the orbit of the planet is aligned in just such a way that you can see, infer the planet going in front of the star and going behind the star. Okay? So what happens when the planet goes in front of the star is you see this little dip in the starlight. Okay? So the amplitude, the width of that depth there, the primary eclipse depth, is just the planet to star radius ratio squared. Okay? It's just the area of the planet over the area of the star, the disks of the planet versus the star. Of course, another situation happens when the planet is just about to hide behind the star. So just in that situation, you see the daylight from the planet and the star, and when the planet disappears behind the star, you're seeing just the star. You subtract the two, so you can get the planet flux alone. Okay, so we see another analogous dip at this situation, and that depth is proportional to the flux received from the star. Here I'm just using a black body function here. This is the brightness temperature of the planet times the area of the planet, or the flux observed from the star. What this is telling us is that when we are seeing the planet transit in front of the star, one can probe the atmosphere of this little annulus, the atmosphere at the day side terminator region of the planet, and when the planet is going behind the star, one probes the day side atmosphere of the planet. Okay? So these are the kinds of observations we'll be using to infer the atmospheric properties of these planets. Now let's get to some real examples. Now, I'll have to warn you before I go in, as I warned at the beginning of the talk, is that just these expressions tell you that the larger the planet or the hotter the planet, the better is the signal. Okay? Which is why most of our observations today have come for giant planets and hot planets. Okay? So I'll refer to these concepts over and over again, so you know where they're coming from. Just these simple expressions here. Bigger and hotter planets have better signals. So let's get to some real world examples. These are showing some of the best spectra to date. This is spectrum of a transmission function observed in this sort of geometry for this planet, HD 209458b. So you see that's the absorption. It's just that as a function of wavelength. So you're seeing this big peak. Now, if you're doing infrared spectroscopy, you know that there is a big water absorption feature in that wavelength range, and that's how we inferred that that peak is due to water in the planet's atmosphere. Okay? So the data points here, just to be sure, the solid curve is a model spectrum, and the data are the observations, obviously, the data with error bars. Same situation in the day side atmosphere, except in this particular planet we don't see water on the day side. These are, again, this is a model spectrum with a water feature. The red is a model spectrum without a water feature, which fits the data better. But this is just to show you that we can get observations in many different band passes across the near and mid infrared for this particular configuration. And when the planet is in between those two situations, one can also obtain thermal phase curves of these planets. Okay, this is showing a model spectrum. The point to mention here is that these hot Jupiter atmospheres they're mostly dominated by molecular hydrogen, but they can also have trace quantities of these various molecules like water, carbon monoxide, carbon dioxide, methane, and so forth. And these features, the molecular features, tend to be broad enough that even with photometric observations, by photometry, I mean you have just this big bandpass and you integrate all the flux in this bandpass and get one point. Okay, that's different from spectroscopy, an example which I showed you in this bandpass. The point to be made here is that even with photometric observations, you can detect these, you can infer the presence of these molecular features because the features are so broad. Okay, you don't need necessarily extremely high resolution spectroscopy to do a lot of this work. It's good if you have better resolution, but we can also make do with slightly lower resolution. Okay, so with that sort of a tutorial, let's talk about what sort of chemicals are we detecting. I'll say up front that by and large, the most robustly detected chemicals in these atmospheres today is water, water vapor. Okay, so let's see what are the kinds of observations we have. This is just for completeness showing a broadband photometric observations for this hot Jupiter WASP 12b. This was in the early days in this field was 5 years ago. In late 2010 to 2011, we had broadband photometric points, no spectroscopy, for about 8 channels for this hot Jupiter. And what all we could do back then was to fit models to those photometric points and still infer, as I mentioned, you could still infer sort of limits on the molecular compositions in this atmosphere just from photometric observations. So you can see this model fits pretty well, and if you want to know what are the limits on the molecular abundances, those are the limits. Okay, you just do a statistical fit, so you can explore the parameter space of water, methane, CO, CO2, and so forth, and you can put constraints on things like oxygen to hydrogen, carbon to hydrogen ratios, and so forth. So this was the first time when we sort of realized that even with photometric observations or low resolution spectroscopy, you can already begin to say something about fundamental quantities like elemental abundance ratios in these atmospheres. So with spectroscopy, you'll only do much better than this. Okay? So this was the early days, and let me zoom right to the present now. These are some of the best spectra obtained for hot Jupiters to date. I'm showing you only 2 spectra out of this extremely large HST program. We thought this was huge. It was a big program with HST, over 100 orbits to look at close to a dozen planets. But only 2 of those planets had any good spectra like this. Okay? So most of those spectra were almost unusable, as you'll see in the next slide. But I think I hope you're convinced that you don't need a model spectrum in this case to infer the presence of this peak. Okay, so we are at a state in this field now where we can see molecular features in these atmospheres very clearly. Not only that, we can actually take these molecular features, these spectral features, and try to infer the water abundance. This is the posterior probability distribution of water abundance in each of these systems, and another system was WASP-12 as well. And you can see these peaks are very, very nicely constrained. So this was the best case scenario in that big program. What are the remaining targets? What do the remaining targets look like? So this was a good signal, and then everything else, you see the error bars are too big. You can fit with flat, straight lines. Okay. So the lesson learned with over 100 HST orbits is that single transits or occultations are not adequate to get these spectroscopic features for most hot Jupiters. Okay, you need really bright stars, and David's going to talk about that, why you need bright stars. So obviously the next thing we did is propose even more orbits, HST orbits, but to look for smaller planets, smaller number of planets. So here we got about 150 HST orbits to look at just 4 planets repeatedly. So this is one example of that, WASP-43b, which has a pretty good signal, but we looked at it with 60 HST orbits, 6 transits, 5 occultations, 3 full planetary orbits, and you can see this nice phase curve. So that's the transit. You can see this ramp up to the day side, and that's the day side eclipse. I'll show you a slightly better representation of this in a minute. Now the spectra, when you bin those, you can see these very nice water features, okay, on the day side and then in the night side. And you can also determine the water abundances, and you can determine the water abundance as a function of phase of the planet. Now let's make things a little bit more interesting with this movie. I hope I can play this. So here we'll see the water feature come into view as the day side is coming into view, and then the spectrum goes down as the night side is going down. Okay? So this is sort of high definition phase resolved spectroscopy of hot Jupiters that is already possible today. But it needs a lot of HST time, but in principle it's possible, and we have demonstrated that. Okay, so that is all I want to talk about the hot Jupiter atmospheres. We know these atmospheres have big signals, we can observe them, we can get good data and so forth. What about smaller planets? Let's go to the Neptunes now. This is showing in the early days again, we had only photometric observations for this hot Neptune, GJ436b. We made some inferences about molecular abundances and so forth. This is for the day side spectrum. Same here. Recently, people have looked at the same planet in transmission when the planet was going in front of the star, and all we could find was, this is with HST, you can see the error bars are really small. These are several tens of parts per million. Error bars, all we could find was a flat line again. Okay, no spectroscopic signal. But all hope is not lost. There was a more recent example of HAT P11b. This is also a hot Neptune, but for the first time we actually were able to detect water vapor in this hot Neptune. This is a really hard observation to make, again using HST, but this detection is at a 3 sigma level, which is statistically significant. Okay, so we have gone down to Neptunes in trying to detect, in successfully detecting water vapor in planetary atmospheres. Now let's look at super Earths. Let's go down even further. This is a super Earth about just about 2.6 times the Earth's radius. In the early days, again, we had these photometric observations, and the latest spectrum was revealed just last year, again with a lot of HST time. Now we are talking about 60 HST orbits here, looking at just the transit, not a full phase curve. And all we could find is this extremely flat spectrum. In our circles, we joke that this is the most expensive spectrum ever for a flat spectrum. So you can see in a completely flat line. So no conclusions there. The best conclusion is that maybe there are clouds in these atmospheres which are blocking the atmosphere from view in the planet's atmosphere. So we don't see any spectral features. Okay. So that is how hard it is to get spectra of small planets, and this is still more than twice the Earth's size, and and about 500 Kelvin temperatures. Okay, so if you're talking about habitable planets, that's going to be extremely hard. It's not possible with HST, maybe not even possible with JWST. Okay, so that's the kind of challenges we are up against. JWST, I should mention, should be able to obtain spectra of such planets around lower mass stars which have smaller radii, so the denominator in the transit depth goes lower, so the signal could be better. But these are our current limits. Okay, now we have talked about some water detections. So what are the implications of these chemical compositions? So we saw this slide where I mentioned that we have constraints on C2O ratios on these objects. Why is the C2O ratio important? Okay. Here I am plotting the C2O ratio on the x-axis and the molecular abundances in an atmosphere, a hydrogen-rich atmosphere, on the y-axis. You can see that this dotted line is at C2O ratio of 0.5, which is the solar C2O ratio. You can see that for high temperatures, 2000 Kelvin, the water is very abundant, right, for this C2O ratio. So is carbon monoxide, and all the hydrocarbons are underabundant. But when you flip the C2O ratio by just a factor of 2, when you make carbon close to the oxygen abundance, you see that the water abundance decreases by 2 orders of magnitude. So that's an extreme effect. So quantities like this, like the elemental abundance ratios, are extremely important to see what sort of chemistry you can expect in these atmospheres. Okay, they can be radically different. Water can drop by 2 orders of magnitude. Hydrocarbons can kick in by 2 orders of magnitude. And since water provides the dominant opacity in these atmospheres, that can have a huge impact on other compounds like titanium oxide, vanadium oxide, and so forth, which also influence your atmospheric dynamics and temperature structures and so forth. I won't go too much in detail into that plot. We have also seen in a previous slide that we are getting these good water abundances and tightly constrained water abundances. Now let me show the same plot in a slightly different way. Here I am plotting the water abundance with the error bars obtained from data. These are for cloud-free atmospheres, the inferences, and their temperatures. Okay? So you can see that for the most part, these water detections are lower than what you would expect if you had a solar composition in the giant planet atmosphere, and much lower than what you would predict for Jupiter in the solar system. Now you notice that for Jupiter we only have a lower limit on the water abundance. It must be shocking to you. I'm saying that we can find water in exoplanets, but for Jupiter we don't know the water abundance. It's actually quite simple. Jupiter is extremely cold. Okay, Jupiter's atmosphere is about 100 Kelvin, so all the water is condensed out of the atmosphere and buried deep in the clouds, in the atmosphere. So if you want to detect water in Jupiter's atmosphere, you actually have to send a probe into the atmosphere. But for hot Jupiters, that's not the case. These are thousands of Kelvin hot, so all the water is in the atmosphere, so you can see it even from our space telescopes. So this is a mind-boggling reality, is that for once, you can measure something better in an exoplanet, a chemical signature, better in an exoplanet than in our own solar system. Okay? that was a slight deviation, but the point being that for a lot of these planets we are seeing, if you assume cloud-free atmospheres, you are seeing that the water abundance is lower than what we would expect for a solar system giant planet. What is causing these low abundances? Again, there are two schools of thought. One possibility is that there are clouds in these atmospheres, or another school of thought is that it could be due to the formation conditions influencing the oxygen abundances. So there are several studies suggesting that this is a planet HD 189733 where people are seeing this slope blueward in transmission, suggesting that there could be some hazes or clouds in these atmospheres causing Mie scattering or particulate Rayleigh scattering in these atmospheres. And there are also theoretical works suggesting that high temperature condensates are possible in these extremely hot atmospheres. Okay, you could have clouds of iron or silicates or aluminum oxides and so forth. So in principle, that is a plausible explanation. If you're seeing low abundances, it could be due to high temperature clouds. The other the other school of thought is that maybe the planet formation is doing something to these objects so that they're accreting less oxygen. Now let me spend a slide on this. This is just a cartoon of a giant planet forming beyond the water ice line, but migrating in two different ways. One either migrating through the disk to reach their very close-in orbits, or got scattered dynamically and ended up in a close-in orbit. Now depending on how far you are from the star and where you form the planet, you can have extremely different carbon to oxygen ratios in the gas, because what's happening is that as you go out in the disk, you're condensing different molecules, water, CO2, CO, and so forth, which means you're depleting the oxygen in the gas. Okay? So the punchline, without going into too much detail, is that depending on where you form the planet and when you form it, the disk itself can have a very different composition, even if the star is solar composition. Okay? So it's natural to think that if you track the planet's history by putting a planet at different distances and migrating through the disk, it could end up with very different chemical compositions than the star. So just a summary of that is we tried recently forming planets in different ways, co-accretion versus gravitational instability, and migrating these planets in along different channels. And we find that we can actually populate this diagram. The C2H is on the y-axis, O2H ratio is on the x-axis. We can, if you see planets with very high metallicity, there are many ways to get them. Okay? Just like Jupiter in the solar system, you just need to accrete enough ices as you migrate the planet to get these supersolar abundances. But what we are finding is that it's very hard to form planets with subsolar abundances. Okay? There are a few pathways that can form planets here, but they all have to involve disk-free migration, which means got scattered and ended up close to their stars. These are still very preliminary works that have been reported. So the spirit I'm trying to convey here is that there is still a lot of scope for trying to use elemental abundances in constraining planet formation, especially for these giant planets. So that's sort of the way in which the field is moving forward. In the remaining couple of minutes, I'll talk about what we can learn about rocky planets now. The atmospheric observations, as we have learned, are very minimal for rocky planets, but nevertheless, let's see what we can learn with the information we have. For the most part, for rocky planets, we have just masses and radii. Okay? So here I plot the mass radius curves for water, silicates, and iron. These are basically taking uniform balls of different compositions. Let's say if I just took an iron ball with a certain mass, what would be its radius? This can be done theoretically, easy to do. So I plot these mass radius curves and I plot several planets here. You can see that by and large, most of these planets below the water curve you can explain with some combination of iron, silicates, and water. Right? So it's a degenerate problem to begin with. So is there anything else in terms of chemical diversity that we could expect for super Earths? Let's see if we can work our way towards that goal. In this particular case, I want to focus on this planet called 55 Cancri E, which sits right above this silicate curve, which means even if you had just a pure silicate planet, you won't be able to explain its mass and radius completely. Okay? So one needs a slightly a layer of water on top of the silicate layer. But the problem is that the planet is 2400 Kelvin. Now imagine trying to have a water layer at 2400 Kelvin. Okay? It's very hard. You can have some sort of a supercritical water state, but you can show that it's unstable to some extent. So I'll cut the long story short. What we have tried here is asking the fundamental question: what if these are not the only chemicals in these objects? Okay, so if you put a carbon-rich composition, for example, that will explain the mass and radius without any water layer. Okay, and you can have a wide diversity in these carbon-rich abundances and explain the mass and radius of the planet. Now, why is this important? It's important because if you have a solar-rich composition, a carbon to oxygen ratio of 0.5 again, you can have silicates and so forth in the planetesimals, rocks. Whereas if you had a slightly carbon-rich composition in the star and hence in the disk, what you end up with is a lot of carbon-rich minerals. And this star, 55 Cancri, was actually reported to have a high C2O ratio originally. Okay? So the punchline here is that when we look at these objects elsewhere, it's important to consider the stellar abundances as well, which may provide us some clues as to what the mineral compositions, possible mineral compositions could be in these systems. Okay, so I think I have run out of time. I'll take 1 more minute to wrap up these quick conclusions. Okay, so I've mentioned that the elemental abundances of the nebula play an important role in the mass radius. Diagram, what I'm showing here is that even if you had just a solar composition object, a solar composition nebula, the composition in the disk is changing as a function of time because the disk is cooling and you hit different condensation fronts as a function of time. So even if you had just a solar composition nebula, depending on where you're forming in the disk, you could have very different carbon fractions in the planet. Okay? So planet formation is extremely non-linear in that sense, even chemically, not just dynamically. Okay? So we must expect a lot of diversity in chemical compositions of these objects as we move forward. So I had a couple more slides, but I'll stop right here. I'll jump to the last slide. The punchline slide, because you all want to hear about habitability. I'll jump straight to this slide. So we talk a lot about habitability in super Earths and so forth. Let me take one step even before that and say, is plate tectonics even possible on super Earths, right? So this is showing plate tectonics on Earth, and you need certain conditions for plate tectonics to happen, like mantle convection, oceanic plates, continental plates, and so forth. Super Earths have temperatures, as we saw, up to 3000 Kelvin, and if you talk about the temperature profiles at such temperatures, most of the silicate is liquid at those temperatures. So you may not even have continental plates to begin with, let alone plate tectonics. Okay? So when we make these statements about plate tectonics, we ought to be taking into account the equilibrium temperatures of these planets and see if it's even feasible to talk about plates to begin with. Okay? So there are all these non-linearities involved, and I'll end with saying that today we know about several dozens of planets sitting in the habitable zones of their host stars, but whether or not these planets are habitable, it's a question that is out there. There are several factors that influence habitability, and we are not even close to even outlining all those factors. I'll just say that the habitable zone, there is a lot of debate even in quantifying what the habitable zone is. It's extremely dependent on what the atmospheric composition of the planet is, which we don't know. Okay? So it's a very nonlinear problem. There is a lot of theoretical work to be done, and the observational work also to be done, and I'll end there. Thank you.